Okay, so good morning. We begin we continue our study of statistical physics. And last lecture we sort of worked out a formula where for the pressure, and actually this is a universal formula, and it's not specific really to the ideal gas, because if you remember, we just used that there was some system and there was some. So we tried to write some. We didn't use too many details in this formula, but we saw that this combination, which is minus kBt times log z, appeared. Okay, and so this I call the Helmholtz free energy. Okay, one thing to remember is that all free energies have the dimensions of energy, and you can check here that kBt has the dimensions of energy. So log is dimensionless, so that's perfect. So F is this thing. And so the idea here is that, and this is the state function appropriate for the canonical ensemble in thermodynamics. Okay. So, by the way, I have shared some simple things on the laws of thermodynamics. It's from this chemistry thing that's called some Chem Libre text or something like that, but it has a nice description of the basic, the four laws, that is 0, 1, 2, 3, okay? And the reason it's called 0, 1, 2, 3, not 1, 2, 3, 4 is because 1, 2, 3 existed first and 0 came later. Somebody said that, logically we needed to have 0. Okay. So this is, so are there any questions about this formula? Okay, good. So now we can ask a question. What is the formula for entropy in the canonical ensemble? Okay, so why is that? I mean, remember, of course, entropy is a state function in which ensemble? Which ensemble you would use where entropy would be the state function?
Microcanonical.
Exactly. Okay, so it's a fundamental quantity there. So, but I'm asking, what is it? What is it in the canonical ensemble? Okay, so of course there is an answer. Okay, so the answer, thermodynamics gives the answer, but can we understand it? In our setting. Okay, this is what I want to. So I'm not answering the question, but I'm saying if you knew your thermodynamics, it would tell you what it should be. Okay, so but I don't want to do that. So the thing we know. So to answer this, I will discuss something, a related thing is equivalence of ensembles. Okay. So this is what I want to discuss. So the first point is that so we have two. Let me just. Okay, so what we see here is that the entropy. So V and N just go for the right. Is that the entropy is naturally in the canonical ensemble is given in terms of the internal energy. Okay, but in this ensemble U is identified with the expectation value of E, right, in statistical mechanics. And so in this thing, so, and we got a formula for this. For instance, this was minus D log. Okay, so, or we can write this as minus D by D beta of, I want to write it in terms of free energy, so I write beta. Okay, so what is happening is that up to some factors, it's a derivative. U is a derivative of f, right? It's given in terms of a derivative of f, and so the thing is, so we need to have some change of variables. So I'm not even answering the question, but I'm just showing you what the issues are. And is that we need to go from here to here or here to here. Okay, we want to go back and forth. And but what is happening in this setup is that we are also going to have a change of variable. Okay, U gets replaced by T. Okay, have we seen anything like this in some other context where we replace one variable by another?
Canonical transformation.
Okay, so canonical transformation or a Legendre. We showed that yeah, canonical transformations. No, that's not quite it. More like Legendre transform. Okay, so
transform.
So recall in classical mechanics. We came across the Legendre transform. Okay, and it was like h, which is a function of p and q, was pq dot minus l, which is a function of q dot, and p. And the relationship between p was expressed in terms of dl by dq dot. This was one way of going. Okay, and second, if you wanted to go the other way, it was to replace q dot was dh by dp, right? So these were the two different ways. One lets you go from Hamiltonian to Lagrangian, and the other one lets you go from Lagrangian. So if you're given the Lagrangian, you define p and then do this, and there's a two-step process. It's not enough to do this. You need to also rewrite everything. Every occurrence of q dot should be replaced by p, etc. Okay. But the feature of this Legendre transform was that extremal solutions, extrema of H got mapped to extrema of L. Okay, so what was it? An extrema of L was Euler-Lagrange equations, and extrema of H was the Hamilton's equation. So they become equivalent. Okay, so this is what extrema get mapped to extrema, and we will see that in some sense this is also that kind of a thing. But this is not the cleanest one, but doesn't matter. Okay, so our idea is, let us try to understand if we have a situation where we can say that both ensembles are equivalent, and we will see that that need not always be the case. Okay, so but there will be situations when we can have two descriptions of the same setup. Okay, one with a microcanonical ensemble and another. Okay, so what we will do is I'll ask a question and I ask you a pause for your answer. So when Okay, so now this is a question to the class. So let me know what you think. What should happen? Yeah, go ahead.
When there will be no heat exchange.
No. One is when the system is isolated. The other
Okay.
is when it's in contact with thermal heat baths. So these two are not quite the same. In one, energy is not fixed, and this thing. So the thing is, so for this to happen, fluctuations in energy should be suppressed. Okay, so energy is allowed to. Okay, so what does that mean? So, and in the last problem set, we saw that it goes like usually fluctuations, relative fluctuations is what we need, which is dimensionless. This goes like 1 by root times the degrees of freedom, roughly. Correct? So, so what is it we need for this number to be small? Somebody, am I connected to the class?
Yes, sir.
Okay.
Can you repeat the question?
Yeah, so the question is what is the situation when relative fluctuations will become small?
Degrees of freedoms will be large.
Yes, so you just need f to be large, reasonably large. Okay, so is that clear? So the point here is, suppose we had just one particle in contact with a heat bath. Okay, then how many one free particle? How many degrees of freedom that has? 3. So in that situation, relative fluctuations will be pretty. We can't. In that case, we cannot have two descriptions. Either the particle is isolated or it's in contact with the heat bath. They are not the same. Okay. So, but if you have an ideal gas with an Avogadro number of particles, then f is of the order of 10 power 23. Square root of f is like 10 power 12. 10 power minus, so relative fluctuation is 10 power minus 11 minus 10 power minus 12, which is very, very, very small, right? Okay, so in such situations, we can actually try to match these things, and that's what we will start doing. Okay, so implies we need f to be large. And intuitively, you can see it doesn't have to be Avogadro's number. Even 10 power 6 might be pretty decent if you're happy with, one part in 10, 1 part in 1,000 or something. Okay, so that's the point. Okay, so let's assume this, and now we can go ahead. Okay, so Z. Okay, I'll go to the definition. Okay, integral over dE, density of states rho of e power minus beta. I'm using the integral form, but it doesn't matter. Whatever. Okay, so now what is happening is that so now we'll assume, okay, let's assume this is true. Okay, so now we can do something, right? So so this what is going to happen is that the dominant, if you wish, E around the same as U, which is the expectation value of U. And there'll be some fluctuations. Okay, so what we will do is that so we can rewrite this thing approximately now. It's not exact. Okay, so what we will do is so this will be some width around small width around U, so rho of U e power minus beta of U. Is this clear? This is an approximation which we are doing. And what we will do is I'll call this quantity, I'll call it omega of, because this is the density of states, which are accessible where around in the small neighborhood around this thing. It's very sharp, and this is what we will do. So we get a nice cool formula which says that Z is approximately equal to omega of u e power minus beta of u. Okay, so let's go ahead. So let me pause here. Is this clear? This is an approximation, but this approximation is pretty good if f becomes large. So the dominant contribution of the integral comes from the neighborhood of that point. So we can just write it like this. Okay. And this was our definition of omega of state. So let's go ahead and take log of this. Let's look at this. We take kb, that's log of z, okay, will be approximately equal to kb log omega of u minus beta of u, which is beta is 1 by kbt, so u by t. Okay, so now question to you is, what is kb log omega of u?
S.
S of u. Okay. So, okay, and what is this quantity? It's minus f by t. Okay, or okay. So this is actually, so we have in some sense derived it, but this is a standard result in thermodynamics. We didn't need it. Have some of you seen this?
Yes, sir.
Okay.
Yes, sir.
Okay, so let's just go back through this argument. So at this point, there is no approximation, and we just using the fact that this is, the correct way to do this integral is by saddle point. And if you remember, rho of e is typically an increasing function, and this is a decreasing function, so there will be a peak. Okay, and that peak will occur again in the set of large numbers, mean, median, mode, everything will become the same. There's nothing bizarre about the whole thing. So okay, that's what we are doing. And so this will, so I just kept some delta E, which is some small wedge around which the fluctuations would be there. And I just said all those guys, we put them in and we just call them approximately omega of u. Okay, so because the reason to write it as omega of u is because now this is an object which we understand from the microcanonical ensemble. So now on the right hand side, we got everything which appears in the microcanonical ensemble, and the left hand side is something in the canonical ensemble, and this is what happens. Okay, so
Sir,
yeah.
in this integral, it would be y-axis is number of states and x-axis is energy, right?
In this integral,
This approximation d rho of u e power minus beta u.
there's no integral in the second step here, right? I've replaced the integral by saying it's some, I'm just taking the contribution at some u, at e equal to u. So this is, let me write it, contribution near e equal to u with some width, which I'm not specifying. Which I write as dE.
Okay.
That's all. Okay. See, we never, even when the system was isolated, we said that we will let it fluctuate in some width. Because if you're giving just one value of energy, especially, that's not something we did even earlier in the microcanonical. We said it's within some fluctuation, some range we should allow. Okay. So this is what we, omega of u, but we never bothered about what was the dE or something. So we just wrote omega of u. Okay. So this is what we get, and we get this nice formula. Okay, so now we can see that we can get a formula for S. So we can use this. Okay, what does it say? So write it like this. So Ts is equal to U minus F S equal to okay. So let's also just remember something. So what is U? U was d by d beta, the minus sign of log z, but I want to write everything in terms of f, so I'll write it like this. Okay, and so this is equal to df minus beta times df. Sorry. There's no minus sign because f has a minus sign, right? So that's so this is what we get. So what we see from this, so we can plug it in here and we get S equal to minus plus F minus F divided by T. So these two cancel. So we get it like this. But this is a little bit ugly because there's beta and T, so we would like to convert back and forth. So I would like to claim that since beta is proportional to 1 by D, you can show that B d by d beta is equal to minus T d by dt. Okay, prove this. Okay. So this up to a sign becomes minus T df by dt, and there's a 1 by T here. So finally we have a formula which says S equal to minus df by dt. This is one formula. We had P equal to minus df by dv. So let me just write what we keep constant v and n. Okay, this is what we get. Okay, so is this clear? This we had derived last time, and now we got a cool, very simple formula for entropy. So this is okay. So we got a nice formula for the entropy in the canonical ensemble. So we derived, now comes the interesting point that look, we derived this when the two ensembles were equivalent. But now the question to you is, suppose I have a situation where I only have a canonical ensemble. What is the formula I should use for S in the canonical ensemble? There's no equivalent microcanonical ensemble. Then what is the formula I have to use? Okay, lot of silence. It will be the same formula, okay, except that you don't have I mean, you just don't go back and compare. There's nothing to compare with in some sense. Okay, because the energy is fluctuating a lot. But I mean, so what? So this is what you will get. And so we get this formula. So now let's do a computation. Okay. So recall, I mean, I'm just looking at writing the formula. Capital Z was 1 by n factorial. Okay, square bracket is little z power n, and there's an n factorial. Okay, and so you work out what log z is. Okay, so you compute log z, then use Stirling's formula. It says that we'll take logs, right? So log n factorial. What is log n factorial? N log n minus n, right? Okay. So this is what you should plug in. And then you can go ahead and you'll get a formula for the free energy by multiplying by kBt, etc. Okay. And so F would be minus kBt times log of Z. So let's just look at that. Okay. So it will become, I'll just write the formula. Okay. If you don't mind. Okay. So key point here is that this n comes from this n log n kind of guy. Okay, n log n you can see here. Okay, so that's where it comes from. And that's it. This is the minus 1. Okay, so is this clear that this is the formula that we get? And so now you will see this n, why the n factorial is important is that we'll go back to thermodynamics. This is an extensive function. Okay, and so this factor of n makes sense. So, but whatever in the square brackets should be intensive. So if you scale n, you scale v together, that should cancel. And so if you did not divide by n factorial, you will see that the extensivity is destroyed. Okay, because now you can see n by v. So n by v is intensive, which is correct. So is t. T is also intensive. Is this point clear? Any questions, comments about this computation? So here's another way of understanding why we need the n factorial. Okay, so now that we have this formula for f, okay, S is, what was S? Minus df by dt, right? Isn't that what we got? Okay, keeping everything else constant. So you can see there are some terms coming. So there's one coming from here, okay, and further there's another t out here. Okay, so there are two places where the t comes, and okay, so let's just do that. So first one is very easy. This t will be Okay, and there was that minus 1 is there. But then if you look here, derivative of this will give you a 1 by t, which will cancel this t, and you'll get a plus 3 half, minus 3 half. So this will just become minus 5 by 2. Okay, so this is the formula for the entropy of a monatomic. I will not say. The first I'm using monatomic. If it is diatomic or something, there'll be other degrees of freedom, so you need to get those contributions. Okay, so this is what we get. But now we can ask, so now can we write a formula for the entropy in the microcanonical ensemble? Okay, so we got this S here is a function of t. It's not a function of u. Okay, so now can we get a formula? So the question to you is, can we get a formula for S where we trade t for u? How would we do that? What is u for this ideal gas?
Three by two nkbt.
Right?
3 by 2 kb.
nkbt. That's all we need to do. Just put 3 by 2 nkbt. So kbt can be replaced. Absolutely. Right? So we just have to change variables, and once we do that, we will get. So what do we know? So we know that kbt is equal to 2 by 3 u by n. If we do this substitution, we'll get a formula, and so I'll write that formula. By the way, I made a mistake. There's a sign error. We have, so this is the formula for the entropy in the micro. So this formula is a name. Sample vector. This is the name of this. So this is a well-known formula. I will pause here and ask questions. So we can also go back and exercise for you.
But there is some noise. Your voice is not clear.
Now, is it clear? No, it's not from me. It's from someone else. Can you hear me? Because I wasn't speaking. Okay.
No, sir. Actually, while you speak, we are hearing a lot of other background noise from that. While you speak, it's not becoming clear.
Oh, since when?
Like 2 or 3 minutes maybe.
So I don't know what to do. I'll try to see if I can increase my microphone thing. Is this better? Is this better? Hello?
Yeah, sir, I think it just got a bit more worse.
Okay. Then let me at least reduce it. Now? Okay, I don't know. I can't figure out where it's coming from then. So let's just continue because we only have a few more minutes. Okay. So the exercise is to compute this directly. Actually, we have the answer from omega. Okay. Or compare. Compute this or compare. One. We have one. And compare. But when I was teaching thermodynamics, I had a very fun exercise. So here we have thermodynamics. Okay. So fun exercise in thermodynamics is to obtain the vacuum. Okay. So I'll share a problem set of mine where I obtain the answer using what can the answer be. And we'll almost get this thing. There'll be some constant factors which we won't get. But we will get the dependence on V, U, N, etc. So we won't get the 5 half for sure. We won't even get the 4 by N, H square N. But we'll get the other dependence on U, V, and N. Right? So up to some additive constant, we will get the answer. Okay. But of course, in statistical mechanics, these constants are also something we can compute. Okay. So I'll pause here for some questions. And see if there is something I can do a little bit more. There's something I wanted to do. Yeah, there's just one small thing I wanted to do. And I just want to stop after that. So in thermodynamics, so I'll give you one expression for the first law of thermodynamics. It is nothing but the conservation of energy. There are many forms of writing it, but I will write it in a particular form. I'm not sure about this sign. Maybe this is a minus, I don't know. So let me just forget about mu for the moment. Okay. Let it be. Okay. Keeping number big. Okay. So this is what we get. So what we see here is that S. So this is same as saying that ds by du is equal to 1 by 2, and it says that ds by dv, keeping u constant, keeping v constant, and this keeping v constant, this is equal to p. Okay. So now what I want you to do is show that starting from f equal to u minus es. Okay, we can show that df is equal to something. So f is a function of t, so that will be pt plus something which is a function of v is kept constant. Okay, so work out what are these values. Okay, so okay. So when you look at this and you do variation, so you see here that in TDS there is du, okay, but out here the du thing should cancel out and it should become only the dt should come. It's exactly again similar. So this is kind of the hint that this is the Legendre transform. So what we have is that we had something which is a function of u and v. I'm forgetting n for now, and we end up with something which is a function of t and v. To do this computation, and it should agree with whatever we knew, with some expressions that we had. Okay, so this should be partial derivative with respect to calculus. We know that this has to be df by. Okay, so we know what these quantities are, but we work it out starting from this body. Okay, so you should see, you should recover the expressions that we wrote for pressure and whatever. Pressure and what is the total? What was df by dt? It was entropy, right? So you get sp. So we just go back and check this thing. So this is the key feature of Legendre transform. This is in a particular sense it's a Legendre transform. But we will see this a little bit more in detail again when we look at, when we will have a lecture or two or something like this. Maybe this week. So I'm done for today. Pause for some questions.
Sir, I think del S del V will be P by T.
Del S?
Del S del V should be P by T, right?
Yeah, correct. Thank you. Correct. Any other comments? Yeah, that's so just go back and do these things. But remember, whatever things we have done it in statistical mechanics, but it should be compatible with whatever we know in thermodynamics, and it is. Okay. So any more questions?